With the proliferation of computationally intensive machine learning applications such as chatbots that perform real-time language translation, device manufacturers often incorporate specialized hardware components to rapidly move and process the massive amounts of data these systems demand. Choosing the best design for these components, known as deep neural network accelerators, is challenging because they can have an enormous range of design options. This difficult problem becomes even thornier when a designer seeks to add cryptographic operations to keep data safe from attackers. Now, MIT researchers have developed a search engine that can efficiently identify optimal designs for deep neural network accelerators that preserve data security while boosting performance. Their search tool, known as SecureLoop, is designed to consider how the addition of data encryption and authentication measures will impact the performance and energy usage of the accelerator chip. An engineer could use this tool to obtain the optimal design of an accelerator tailored to their neural network and machine learning tasks. When compared to conventional scheduling techniques that don't consider security, SecureLoop can improve performance of accelerator designs while keeping data protected. Using SecureLoop could help a user improve the speed and performance of demanding AI applications such as autonomous driving or medical image classification, while ensuring sensitive user data remains safe from some types of attacks. A deep neural network consists of many layers of interconnected nodes that process data. Typically, the output of one layer becomes the input of the next layer. Data are grouped into units called tiles for processing and transfer between off-chip memory and the accelerator. Each layer of the neural network can have its own data tiling configuration. A deep neural network accelerator is a processor with an array of computational units that parallelizes operations like multiplication in each layer of the network. The accelerator schedule describes how data are moved and processed. Since space on an accelerator chip is at a premium, most data are stored in off-chip memory and fetched by the accelerator when needed. But because data are stored off-chip, they are vulnerable to an attacker who could steal information or change some values, causing the neural network to malfunction. Manufacturers can protect data by adding authenticated encryption to the accelerator. Encryption scrambles the data using a secret key. Then authentication cuts the data into uniform chunks and assigns a cryptographic hash to each chunk of data, which is stored along with the data chunk in off-chip memory. When the accelerator fetches an encrypted chunk of data known as an authentication block, it uses a secret key to recover and verify the original data before processing it. But the sizes of authentication blocks and tiles of data don't match up, so there could be multiple tiles in one block, or a tile could be split between two blocks. The accelerator can't arbitrarily grab a fraction of an authentication block, so it may end up grabbing extra data, which uses additional energy and slows down computation. Plus, the accelerator still must run an cryptographic operation on each authentication block, adding even more computational cost. With SecureLoop, the MIT researchers sought a method that could identify the fastest and most energy-efficient accelerator schedule, one that minimizes the number of times the device needs to access off-chip memory to grab extra blocks of data because of encryption and authentication. They began by augmenting an existing search engine, TimeLoop. First, they added a model that could account for the additional computation needed for encryption and authentication. Then they reformulated the search problem into a simple mathematical expression which enables SecureLoop to find the ideal authentical block size in a much more efficient manner than searching through all possible options. Finally, they incorporated a heuristic technique that ensures SecureLoop identifies a schedule which maximizes the performance of the entire deep neural network rather than only a single layer. At the end, the search engine outputs an accelerator schedule which includes the data tiling strategy and the size of the authentication blocks that provides the best possible speed and energy efficiency for a specific neural network. When tested in a simulator, SecureLoop identified schedules that were up to 33.2% faster and exhibited 50.2% better energy delay product, a metric related to energy efficiency, than other methods that didn't consider security. The researchers also used SecureLoop to explore how the design space for accelerators changes when security is considered. They learned that allocating a bit more of the chip's area for the cryptographic engine and sacrificing some space for on-chip memory can lead to better performance. In the future, the researchers want to use SecureLoop to find accelerator designs that are resilient to side channel attacks, which occur when an attacker has access to physical hardware. For instance, an attacker could monitor the power consumption pattern of a device to obtain secret information, even if the data have been encrypted. They are also extending SecureLoop so it could be applied to other kinds of computation.